We're going to finish up section 3.3 with one very important example. And so to get started, let's recall more or less the last thing we proved in the previous lecture, which is that if P is a polynomial, then the limit as x approaches 0 of P of 1 over x times exp of negative 1 over x squared is equal to 0. So here is the example function that I have been talking about. So let's let f of x, this is a piecewise defined function. It's going to be exp e to the power of negative 1 over x squared if x is positive, and it is going to be 0 if x is negative. And then the claim is that then f is a smooth function on the real numbers. That is the kth derivative of x exists and is continuous on all the real numbers for all natural numbers k, that is all non-negative integers k. So let's prove this. That is, we're going to prove that this example has the property I just claimed. So here's the first thing to observe, and that's that any derivative, if x is negative, then any derivative, then f of x, f prime of x, f double prime of x is 0. F is a constant, f is 0 in a neighborhood of x, so the derivative's derivative, they're all 0. And I think we will stipulate that at this point that is obvious, although if it's not obvious to you, ask me and I'll explain more in class. The second thing I am going to do is I am going to claim is that if k is a non-negative integer, let's let n naught be the natural numbers plus 0, so I don't have to keep writing non-negative integer, then there is a polynomial pk such that the kth derivative of f is p sub k of not x but 1 over x times exp negative 1 over x squared, and that's for all positive numbers x. And then here is how we prove our claim. So let's let p naught of x be the polynomial 1. So with this value of p naught, the claim is true by definition of x. For k k equals 0. Now let's suppose the claim is true for some k. Then if x is positive, let's go ahead and differentiate our f. F with k plus 1 derivatives at x. That's f with k derivatives, and then you take one more derivative. And then and then we just use the product rule. Pk of 1 over x. So let's write this out as the derivative. Then pk of 1 over x. X minus 1 over x squared. And then that equals, by the product rule, you've got pk prime of 1 over x, and then chain rule, negative 1 over x squared, x minus 1 over x squared. And then we have to add to that pk of 1 over x, and then x minus 1 over x squared. And then the derivative of x is x, and then the chain rule, we get a 2 over x cubed. So the claim is true. So that is, we're going to let pk plus 1 of, let's not call it x, let's call it y, is pk prime of y times negative y squared. And then we add to that 2 and then a y cubed pk of y. And then if pk is a polynomial multiplying by y cubed, it's still a polynomial, and the derivative of a polynomial is also always going to be a polynomial. So since pk is a polynomial, pk plus 1 is a polynomial. And then we've got that our formula for k plus 1 and derivatives works. And by induction, the claim is true for all k. And then using the result from the previous video, we have that the limit as x goes to 0 of the kth derivative of x, the limit from the left is always 0. The limit from the right is a polynomial in 1 over x times e to the negative 1 over x squared is 0. So the left-hand limit is 0. The right-hand limit is 0. And then by a homework problem I didn't actually make you do, but it's nonetheless fairly straightforward, the total limit is 0. So we've got that the limit exists for all negative numbers, the limit exists for all positive numbers. Now we just need to show that the function actually has the right value at 0 for all k. And this is another proof by induction. So the claim is true if k is equal to 0, and that's just from the definition to f. F with 0 derivatives is just f, and f of 0 is just 0. All right, and then induction argument is usual. Let's suppose the claim is true if for some k, then fk plus 1 of 0, let's write this out using the limit definition. Kth derivative of x minus the kth derivative of 0 all over x minus 0. All right, now let's write out the left-hand and right-hand limits. Limit as x goes to 0 from the right, fk of x minus fk of 0 over x minus 0. That is the limit as x goes to 0 from the right, but 0 minus 0 over x minus 0 is just 0, so that's not a problem. Limit as x goes to 0 from the left is a little bit trickier. Limit as x goes to 0 from the right. Then that 1 over x minus 0 I'm going to write as a 1 over x. And then fk of 0, we remember, is just 0. That is our induction hypothesis. So I just need the fk of x, which is also known as pk of 1 over x, x minus 1 over x squared. And then pk of 1 over x times pk of 1 and over x, that is also a polynomial in 1 over x. So this limit equals 0 by the result from the last video. So fk plus 1 of 0 equals 0. And this, and if you put our three claims together, we see that our function is indeed smooth. It has infinitely many derivatives everywhere. And let's look at this function then for a minute. So this function is 0 up to 0, and all of its derivatives at 0 are 0. And then it goes up and it approaches an asymptote at 1. Never actually quite it gets there. So the Taylor series for f at 0 is, we just saw that all the derivatives were 0, so the Taylor series is fk of 0 over k factorial x to the k is just 0. So this is an example of a smooth function that doesn't agree with its Taylor series. And people do all kinds of nifty tricks with this function. So for example, let's let g of x be f of x divided by f of x plus f of 1 minus x. Your denominator is positive if x is either positive or less than 1 or both, so this is smooth. So g is also a smooth function on the real numbers. And then g of x is 0 if x is less than 0. And g of x is 1 if x is greater than 1, suppose less than or equal to 0. So this is a function that goes that is smooth, but actually gets from straight line at 0 to straight line at 1, and then is just a smooth transition between them. So you can get smooth functions that go from any value to any other value you want if you find that they're useful. Now we're going to start section 3.4, and section 3.4 is entitled Improper Integrals. And what this is all about is we want to integrate. That is, we want to define things like, the integral from 0 to infinity of e to the minus x, or the integral from 0 to 1 of 1 over the square root of x. Now, if you remember all the definitions of integrals we've seen, it's always a bounded function over a closed bounded interval. So that's the problem with this integral of e to the minus x thing is that you're trying to integrate over an unbounded interval. And 1 over square root of x, that is not a bounded function. So we would like to define what it means to integrate a function on a function like this, an unbounded function or a nice bounded function on an unbounded interval. So here is how we define this. Here is our definition 3.4.1. So let's let AB be an open interval in the real numbers. And I want to emphasize that we are allowing the case where one or the other of the endpoints is infinite. So that's less than or equal to infinity, not less than infinity. And then we say that if f is a function defined on our open interval, then we're going to define f is locally integrable on this interval from a to b if whenever you have a closed interval contained in AB, you've got a closed bounded interval that's a subset, and that means A is strictly less than C, and D is strictly less than B. We have that F is bounded on this interval, and also F is Riemann integrable on this interval. Now we defined Riemann integrable to be a Riemann integrable on a closed bounded interval. You have to be bounded, so this boundedness assumption is sort of optional. Well, it's redundant, but I thought I'd write it down just to emphasize this is something that we are requiring. And then we say that F is integrable or improperly integrable on this interval from A to B if we have that. First off, F has to be locally integrable. And the next thing we want to require is that this nested sequence of limits has to exist. And this means that locally integrable means the integral from C to D exists. But it also means that this limit exists for all numbers C in our interval from A to B. And that if you take the limit of the limits, that thing has to exist. Sorry, one more thing to specify. We also need this integral to be finite. So we want all of our limits to exist, all of our limits to be finite, and this is to avoid this example. So something like f of x is 1 over x minus 1 over x minus 1. So that is, would look something like this. The integral here with then the integral, the area under the curve over here from 1/2 to 1 is infinite. And the area under the curve here from 0 to 1/2 is infinite, except it's over the curve, so that would be a negative area. Then the integral from 0 to 1 of f is infinity minus infinity is an indeterminate form. So we don't want to say we don't want to call this thing integrable, because infinity minus infinity, we really don't like that. We don't want to say that that's a good function, that that's integrable. Let's work through one example of this. So let's let f of x be e to the minus x. And we want to show that f is integrable on the interval from 0 to infinity. Then f is bounded and continuous. So by, well, we'll claim 3.1.8, but let's go ahead and cite theorem 3.1.7 because it's easier to find in your book. F is Riemann integrable on C to D for any closed bounded interval. So f is locally integrable on the interval from 0 to infinity, but whatever you really want. And then we have that the limit as d goes to infinity, integral from c to d e to the minus x dx. That's a simple Cal 1 integral. We will not bother with this e to the minus c minus e to the minus d. And then when we take the limit as d goes to infinity, we're going to get 0, and that, recall, is by theorem 3.3.4e. Sorry, the e to the minus d part is 0. The e to the minus c just hangs out front. And then when we take the limit as c goes to 0 from the right of that limit, that's the limit as c goes to 0 from the right, e to the minus c. And then because the exponential function is continuous, that is just e to the 0 is just 1. So f is integrable on the interval from 0 to infinity. And let's give you an example of a function that is locally integrable but not integrable. So let's let f of x be 1 over x squared times the sine of 1 over x. And I'll point out if in case you've forgotten an awful lot of your techniques of integration, that this happens to be the derivative of the cosine of 1 over x. Then f is continuous on the interval from 0 to infinity. So f is locally integrable because it is integrable on any closed bounded subset, any interval from C to D, as long as C is positive. But if you take the integral from C to D of f, what you get is cosine of 1 over C minus 1 over D minus cosine 1 over C. So then if you take the limit as D goes to infinity, well, I suppose if you take the limit as D goes to infinity on both sides, what you end up with is as D goes to infinity, 1 over D goes to 0, so cosine 1 over D goes to 1, so that's 1 minus cosine of 1 over C. So the limit as C goes to 0 from the right, and then the limit as D goes to infinity, integral from C to D of f, that's the limit as C goes to 0 from the right, cosine 1 over C. And that does not exist. So f is not integrable. One over x is another classic example of a function that's locally integrable but not integrable. 1 over x, you can sort of work around it. You can say that the integral of 1 over x is equal to infinity if you're very careful, but this example, you can't say that the integral exists even if you're willing to say that integral of infinity counts as existing. So here is a proposition that may shed a little bit more light on what exactly it means for a function to be integrable. And in particular, you notice we've got two limits going on. One of the points of this proposition is that it doesn't matter which order those limits go in. Let's let f be a function from an open interval, defined on an open interval, and we're going to say that it is locally integrable. And let's let x be just any point in this interval. Because it's an open interval, we know it's not an endpoint. Then the following statements are equivalent. You will hear this phrase a lot in mathematics. It's when we give you a long list of things, and if any one of them is true, all of them are true. If any one of them is false, all of them are false. So first, this exists, this limit in the definition of integrable that exists and is finite. That is one of our equivalent conditions. That's true if and only if the limit exists if you do it in the other order. And our third equivalent condition, and this is actually the one that's going to be easiest to deal with, is that if you just pick your point in the middle and take your limits of integrals on the two sides, those both exist and are both finite. And furthermore, if our equivalent conditions are true, then we have that all of the limits are equal to each other. So let's prove this. So first off, let's notice that if X and C and D are all points in this open interval from A to B, then F is Riemann integrable on the closed interval from whichever of them is smallest up to whichever of them is biggest. So by exercise 3.1.10, we have that the integral from C to D of f, that's equal to the integral from C to x of f plus the integral from x to d of f. Furthermore, all three integrals exist because we're assuming that f is at least locally integrable. So furthermore, we have, let's notice that the limit as d goes to b minus of this piece, this integral doesn't care what d is at all, so the limit is guaranteed to exist, and we know what it is. It's the integral from c to x. So we have that the limit as d goes to b minus integrals from c to d of f equals integral from c to x of f plus the limit as d goes to b minus integral from x to d of f if either side exists, if either limit exists. So if option C is true, we assume that this limit exists. If option A is true, we assume that this limit exists for any particular C. So in either case, if the first limit exists, so we've got that our D limits exist on either side. And what's more, we've got something very nice written there. Furthermore, if their limit exists, so under the same conditions we've just written out, I guess I won't write them again. The limit as C goes to A from the positive side of this complicated thing. It's a complicated thing, but it doesn't care at all what C is. It's equal to that constant and exists. So we have that. Let's take the limit of the thing we wrote above as C goes to A from the right. That is the limit as C goes to A from the right of the first piece. And then we don't have, and then there's the second piece. So if either exists. So if our right-hand limit exists, meaning if this piece exists, then we can, then our right-hand side is the sum of two limits, so it must be the limit of the sum. And therefore our left-hand limit has to exist. And if our left-hand limit has to exist, well, we could always just take this piece here, move it up. We could always just take this piece here, move it over to the other side. We'd have a difference of limits, which is the limit of the differences. So the end of the day is that A and C are equivalent. And we've got our first equal sign, and I think I will not drag you through this. We'll just notice that similarly, B is equivalent to C. And also, we have established shown the limits are equal. That is, we have proven the thing written at the end of the furthermore, and that completes the proof.